Okay, least square regression unit, day 3. Another way to evaluate how well a least square regression line models a set of data is to consider the value of r squared, which is almost my favorite value. Okay, it is called the coefficient of determination, and it is a measure of the proportion of variability in the y variable that can be accounted for by the linear relationship between x and y. I love this definition. For example, at a pizzeria, the price of a large pizza is a variable. That is, there is variability in the cost of the large pizza depending on how many items are included on the pizza. Suppose that a large pizza sells for $8 plus $1.50 per topping. If we were to plot this, okay, we'd have 0 toppings, an $8 pizza. 1 topping, a $9.50 pizza. 2 toppings, $11 pizza. And they would fall exactly on the line, okay? The only thing that's changing the price is the number of toppings. In this case, the number of topping accounts for 100% of all variability, therefore r squared equals 1, or 100%. Okay? We want to calculate the coefficient of determination for the height and weight data from last time's lecture. Well, we actually already did that. And if we go back right here, our r squared was 0.728. Or approximately 72.8%. And what that claims, okay, is that 72.8% of the variability in height, or excuse me, in weight, can be accounted for by how tall the person is. The rest of it might be how big of a bones they have, how much they eat, etc. Okay? And we're going to talk about a little bit by hand way to find r squared. Okay, to measure that, we know how to find r, so of course we could find r by hand and then square it, but that's an ugly process. So let's look at this way, it's slightly better. To measure the total variability in weight, we measure variability of weight of y from its mean. Okay, this is the first part of finding standard deviation. Again, I'm scrolling, excuse me, that we did right here. But we were calling the same variable x because we hadn't talked about the height yet. We were just talking about the weight. Okay, and so that's that top part right there. Every weight minus the average weight. Okay. Excuse me. So that's what we have here. And so I've got our weights listed down, or some of them, but at least this time they are properly labeled as y. Okay, because they're what we're trying to predict. And the way we could find that is add them all up and take every value minus the average and square it and add them all up. Or again, okay, we could find the average. So notice this has the average in it. So I went back to last time's lecture and we said that the average weight of our students was 153.6. So what we could do is every value, the first weight of the student we measured, minus the average, squared, plus ... I'm not willing to do that. Oh, and you can see here that I had covered that up. Every weight minus the average squared plus the next weight minus the average squared. I'm not willing to do that, but I can have my calculator do it. So if you look, my weights were in list 1 because that was the first thing we talked about, even though they were the y's. So what I'm going to tell list 4 to do, this is just a side note, is say take list 1 and minus from it the average, which we said was 153.6. There it is. Now I can go to stat, calculate, one variable stats, and have it figure out for me list 4 the sum of all of those values squared and added up, and that is, I'm going to move this 14096.4. Okay, so that was taking the sum of all of these values squared and adding them up. All right. We do not consider the x value at all when finding the SS total. Okay. Note that this is the same quantity that we used when we calculated the standard deviation for weight alone. Okay. We can also measure the variability in weight that still remains after we factor in x, the height. So this was that whole residual thing. And we did this already. I refuse to show you again. That is right here. Okay, y minus the residual squared. So one was with average and the other was with residual. So 38, 28.9. And why do we care? Because if we take this total and divide it by this total, we'll get something that'll lead us to r squared. So 38, 28.9 divided by 14096.4. Okay, and that'll give us about 2716. I'm going to move this out of the way. Okay, so it describes the proportion of variation in the weight that is still unaccounted for after using height to predict weight. That's the part that we don't know. How much do they eat? Do they run big boned? Maybe they got on the scale and they have stuff in their pockets. I don't know, but that's the stuff that we don't know. Okay, using addition of variables to predict weight, i.e. waist size or gender, would make this ratio smaller, but that would be a multivariable regression and we won't do that. But if we think about it, r squared tells us how much the x and y, the x does account for it. So if we took this value and subtracted it from 1, we'd get the accounted for part. And we get about 0.7284, which although that was our r squared, this was the part that it is accounted for. So the linear relationship between weight and height accounts for 72.8% of the variability in weight. Okay, using the TI-81 to calculate r squared, you already know how to do this. Okay, I'm not even going to do it. You know. Okay, so what is the relationship between r squared and s? Well, both measure how well a line models the data. Okay, r squared has no units and is expressed as a percent between 0 and 100%. So for that last example, okay, the variability was 72.8. So we're saying that 72.8% of the change in weight could be accounted for by the variation in height. Okay, s is expressed in the same units as the response variable. For example, we said that our average error would be 21.88, or our standard deviation of the errors would be 21.88, meaning our predicted values could be plus or minus 21.88 pounds on average. Okay, and again, that was that height weight one. Here is my favorite one. It will be forever known as the pig poop one. And it's an example problem with the correct interpretation of r squared that I always want you to use. Okay, assume that you are an environmental scientist, okay, and it's probably done by grad students, and what they've done is over the years from 88 to 97, they went out and took estimates of the swine population in a local area. Okay, so those estimates are here. And at the same time, they took measurements of atmospheric ammonia. And I'm not sure how they got those measurements, if it's always in the same spot or whatever. These are always questions you would want to ask. Did they block for it? Was it a random sample of, swine and a random sample of atmospheric ammonia? I don't know. But now that we have our data and you want to ask those questions, I've gone ahead and graphed it. I made our line of best fit. Okay, so we can see that with 0 atmospheric ammonia, or actually, let's see. So what are we saying? We're saying that they're thinking that the swine population may be contributing to the amount of atmospheric ammonia because swines poop and poop makes ammonia. Okay, so we have our resultant variable, right? And then the one that is our one causing stuff. All right, so here's our line of best fit and our R squared. So these are some questions I was asked. The value for the correlation, or how I might talk about it, the value for the correlation coefficient for this data is 0.85. Interpret this value. How do I know that it's 0.85? Well, I have an R squared at 0.7232. If I took the square root, I could get plus or minus 0.85. But R gives you the slope, so it would have to be 0.85. Okay? And then according to the scale given in class, which I will give you in class, since the absolute value of R is greater than 0.8, we're going to say it has a strong linear correlation. Okay? You can see by the scatter plot, and because R is 0.85, notice that I also mentioned the scatter plot, that there's a strong positive linear correlation between swine population and the amount of atmospheric ammonia at swine farms. Which means that as the swine population grows on the farm, so does the amount of atmospheric ammonia in the area at a rate of 0.1325. Okay, at a rate of 0.1325, well, yeah, that's my slope. Okay, that's my rate per 1,000 swine. I would say that more pigs equal more pig poop, which equals more ammonia in the environment that can contaminate water quality. So maybe this whole study was started because there was a worry of water quality, and this is how they use this math in the real world. Okay, here's the key thing. What percent of variability in atmospheric ammonia can be explained by swine population? You must memorize this. Okay, the coefficient of determination is R squared 0.723, which means that approximately 72.3% of the variability in atmospheric ammonia can be explained by the variation in swine population. And I much prefer the way the word explained or accounted for than caused, because again, we really don't know caused. Okay, so memorize this wording. I promise it will haunt you. Question 3 that we'd ask ourselves: are there any unusual aspects of the data we need to consider before making predictions of the model? I'm going to quickly take you back to the McDonald's data. Okay, we may need to consider if we have some clustering going on, if it's a good fit, or if we have two separate sets of data, anything that might be unusual. Or maybe we have really good stuff, but then make a point over here that's kind of like an outlier, would have a lot of leverage. Like if we were to draw a line in, it would look like this if we didn't have this point. Okay, but if we do have that point, the line's going to get moved. So those are things we have to think about. Okay. So that covers question 3. And then in summary, any point that stands apart from the others is called an outlier, like that lower pink point I just showed you. Since the least square regression line must pass through the point x bar, y bar, and we'll break that into your head, points that are separated in the x direction can be particularly influential. We say they have high leverage. We will play with that in class. When a point with high leverage lines up with the rest of the data, the line won't change very much, but the correlation will be stronger. You should read these a few times. When a point with high leverage does not line up with the rest of the data, it could have a large effect on both the line and the correlation. Note, points with high leverage often do not have large residuals since they pull the line close to them. Okay, we'll play with this output later. Finally, understanding computer output. Okay, it looks like I am running out of time, so we will start homework 4 in class and finish this part of the notes. Thank you.